Inshallah, I'll continue today what we have from where we stopped in the last time. Last time we introduced the Shabab to the fuel air cycle, and we said this cycle is a kind of modification of the standard air cycle, by which we can improve the efficiency a little bit. We have developed the efficiency for the Otto cycle, for the standard Otto cycle. We have developed the efficiency to be eta thermal is equal to 1 minus 1 over R to the power K minus 1. So based on the air standard cycle, Shabab, this efficiency is only function of the compression ratio. It does not take care actually about the effect of fuel or the fuel to air ratio or the equivalence ratio. And also in this cycle, we don't have combustion even. Just we assume we add heat under constant pressure and we reject heat under constant. We add heat under constant volume at the top dead center, and we reject heat when the piston approaches the bottom dead center and also under constant volume. But it does not take care of combustion, and also the charge is considered as only air. So we don't have in this case the effect of the fuel, or the effect of the operating condition, operating equivalence ratio on the efficiency of the Otto cycle. As you can see, the efficiency here, Shabab, is only function of the compression ratio. It does not take care about any other effect in this case. And that's why we said we can move to a little bit modified cycle. Still, it is a standard cycle as well, but we call it the fuel air standard cycle. In this fuel air standard cycle, Shabab, as the name indicates, in this case, the charge is a mixture, in this case, of air plus fuel plus some residual gas. Some residual gas, Shabab, from the previous cycle. When we have the engine, is that during the exhaust stroke, the piston is moving up, the exhaust valve is opening. When the piston reaches the top dead center, still in this residual gas in this clearance volume, still some residual gas are there. So we'll consider those residual gas in the charge in this case. Unlike the case, Shabab, of the standard cycle. In the case of the standard Otto cycle, the charge was considered only as air. In this case, I will consider the charge as air plus fuel plus some residual gas in this case. And also the system in the standard Otto cycle was a closed system. We don't have valve, we don't have intake valve, we don't have exhaust valve. Here the system, we will consider the system as open system in this case, in the fuel air cycle. Open systems, that mean we have valves in this case. We have intake valve and we have exhaust valve. Also, in case if you have of the air standard Otto cycle, we don't have combustion, just we have heat addition. Then in this case, we will consider the combustion of air plus fuel. Still, this combustion, we call it instantaneous combustion, because it happens actually once the piston approaches the top dead center. If you look at this cycle on the PV diagram, if this line is representing the top dead center, that line is representing the volume at the bottom dead center. Starting the process from process number 1, we have the isentropic compression process from 1 to 2, in which we have a compression water is added, was applied actually on the piston from the crankshaft. And then in this case, under constant volume from 2 to 3, we have in this case the combustion process. But this combustion, is an instantaneous combustion. Just it take place once the piston approaches the top dead center. We will initiate the combustion using the spark plug. So the combustion will take place instantaneously at no time. And in this case, the pressure will rise to 0.3. And in this case, as the pressure rises at the minimum volume, which is the clearance volume in this case, that means this pressure actually will be the maximum pressure in this case. This is for the fuel air cycle. Still, in this case, we don't consider heat addition, just we consider the real case. We consider the combustion process. The heat will be added due to the combustion process. We don't have external heat addition. Okay? So in this cycle, we have considered the mixture, the real case mixture. Working fluid is air plus fuel plus residual gas. System is open system, so we have intake valve and exhaust valve as well. Instead of heat addition, we have in this case combustion process. But still, as you can see, still the processes are standard processes. So the process from 1 to 2, still it is isentropic compression. So delta S is equal to 0. And isentropic means what, The process is what? Reversible, and the process is adiabatic. And this is a kind actually of a reversible process. So still we do have some assumption. But in this case, at least we have improved the cycle. We have considered the combustion. We have considered the real fuel plus air plus residual gas mixture, and we have valves in this case. Also, شباب, still we have another assumption that we assume all processes are adiabatic. So we assume actually this engine is just an adiabatic engine. We don't have, what does it mean adiabatic, شباب? All processes we don't have heat transfer exactly. So I will assume that I have an adiabatic engine. We don't have all of these processes from 1 until we get back to point 1 through the whole cycle. All processes are adiabatic. So the heat transfer is equal to 0 in this case. That means that this combustion is also what? Adiabatic. Adiabatic combustion, that means the temperature T3 is equal to what? After the combustion process, if we have adiabatic. Yes, Mustafa?
Adiabatic flame temperature.
Exactly. So the temperature T3 will equal to the adiabatic flame temperature in this case. But we have in this case, شباب, constant volume combustion. In case of constant volume combustion, in this case, the adiabatic flame temperature, how we can calculate it? We said Q minus 1 will equal to what? For constant volume, it will be H or U?
U.
It will be exactly U. U product minus U reactant in this case. So we have the system is adiabatic for the combustion process. Instantaneous combustion under constant volume work is equal to BdV, integration of BdV. The volume is constant in the combustion process, so the work is zero. So under this condition, U product will equal to U reactant, or U2 is the same as U3 in this case. Or we can say, شباب, if you remember, U is equal to insoluble formation plus delta H minus R bar T at point 2. That will equal to the same insoluble formation plus delta H minus R bar T at point 3. But at point 2 and point 3, point 2 the charge is air plus fuel plus residual gas. And at point 3, those are the reactant, air plus fuel. So what about point 3, شباب? Those are the combustion product. That means in this cycle, شباب, I have to write down the combustion equation. In this case, for any fuel, like let's say if we have isooctane, C8H18 at a given equivalence ratio or excess air factor, lambda gamma O2 plus 3.76 M2, then we can have the product CO2 plus H2O plus M2 plus O2, all of this. So those are the reactant, okay, which are at point number 2, okay, and those are the product which should be at point number 3. So when we apply the first law for the process from 2 to 3, we can say U product will equal to U reactant, or U2 will equal to U3. Or we can say U product will equal to U reactant, which is the summation of number of moles for each component in the product, will equal to the summation of number of moles for each mole in the reactant, multiplied by insoluble formation plus delta H minus R bar T, like what we have learned before. So in this case, such as in case of fuel air cycle, as you can see, we have considered the combustion is instantaneous. It takes place at constant volume, and all processes are adiabatic. So we have adiabatic combustion. So the temperature T3 should equal to the adiabatic flame temperature. And to calculate this adiabatic flame temperature, I can apply U product will equal to U reactant, or U3 will equal to U2. Write down the combustion equation, and based on this combustion equation, we can calculate the maximum cycle temperature T3. In the example, شباب, that we have solved on the Otto cycle, standard Otto cycle, I have given you the maximum cycle temperature, which is T3. But in this case, in the fuel air cycle, I will not give you the maximum cycle temperature. You have the combustion equation, apply the first law analysis, U product equal to U reactant, then I can calculate T3, which is equal to the adiabatic flame temperature, which is the maximum cycle temperature in this case. Okay, is that clear, شباب?
Yes.
Right. This is شباب, the main difference between the fuel air cycle and also the air standard cycle. In the fuel air cycle, as you can see, you have to write down the combustion equation depending on the equivalence ratio. We have to write down the combustion equation, and then we can calculate the adiabatic flame temperature. That means, يا شباب, the analysis of this cycle depends on actually the equivalence ratio and the fuel to air ratio in this case. Not only function of the compression ratio are like the standard fuel air cycle in this case. Like for process from 1 to 2, we said this is isentropic compression delta S is equal to 0. If you apply the first law, Q minus work equal to delta U. This is the compression work. We said all processes are adiabatic. Then we can say the compression work will equal to U1 minus U2, kilojoule per kilogram. Okay? Like for process from 2 to 3, this is adiabatic combustion. So heat transfer is equal to 0. Work is equal to integration of dV. The volume is constant, so dV will equal to work will equal to 0. Q minus work will equal to delta U. Those are 0. Then we can say U2 will equal to U3, or we can say U product, as we used to do, will equal to U react. And in this case, the temperature T3 will equal to the adiabatic flame temperature, and that has to be calculated based on the combustion equation in this case. I have to write down the combustion equation, apply U product equal to U react, and then I can calculate the maximum cycle temperature in this case. Then the process from 3 to 4. Still in this case, also we have isentropic expansion process. So process from 3 to 4. Isentropic expansion, so delta S is equal to 0. Like this process, Q minus 4 will equal to delta U. The process is adiabatic, so the expansion work will equal to U3 minus U4, kilojoule per kilogram. This is the specific value of the expansion work in this case. Type at point number 4, شباب. At this point, once the piston at the end of the expansion stroke, once the piston reaches the bottom dead center, the exhaust valve will open in this case, at this point. Once the exhaust valve open, here actually the pressure is higher than atmospheric pressure. So in this case, the volume inside the gas, part of the gas will just be pushed out of, to go outside of the piston, to go outside of the cylinder in this case, and the pressure will be reduced inside the cylinder until the pressure approach the atmospheric pressure. So during this period, once the exhaust valve is open, some heat is rejected, and the exhaust gases will be leaving the cylinder in this case, affected by the high pressure inside this cylinder at point number 4. And this is what we call the blow down energy, because still the pressure inside the cylinder is higher than the atmospheric pressure. And the gases will continue the expansion outside the cylinder. So it will continue isentropic expansion until it reach, let's say, 0.5 bar or 5 prime. This 0.5 prime, at which the pressure is equal to what? Atmospheric pressure. But this expansion is outside the engine. This is atmospheric expansion of the exhaust gases under high pressure. It will expand outside the engine until it reaches 0.5 prime, at which the pressure is equal to what? The atmospheric pressure. Okay, we call this energy, شباب. This is the energy, the expansion outside the engine. We call it the blow down energy. Blow down energy, which is the energy lost due to opening the exhaust valve at a pressure higher than the atmospheric pressure, so that the gases will be expanding outside the engine until the pressure actually approaches the atmospheric pressure value. So if this expansion inside the engine, we should benefit actually this amount of energy in this case. But actually, once we open the exhaust valve under high pressure, the gases will be leaving, and it will continue the expansion outside the engine until it reaches 0.5 prime. And this expansion, the area under the curve, we call it the blow down energy, which is a kind of a losses from the losses inside the engine. So let's say this is 0.5 prime, and this is actually 0.5. The piston is at the bottom dead center. The pressure inside the cylinder is almost atmospheric, so the piston will be moving from the bottom dead center to the top dead center until actually it reach, let's say, 0.6. Okay, so at 0.6, the exhaust valve will be closing. and the intake valve will be opening in this case at point number 6. Once the intake valve is open, so the pressure will be equalizing inside the cylinder under constant volume, and the pressure will drop suddenly to 0.7, and then which is the pressure شباب during the intake stroke while the piston is moving down. So if the piston is moving down for a naturally aspirated engine, once the intake valve is open and the piston is moving down, so it creates a vacuum here. So this pressure شباب is less than the atmospheric pressure. So if the exhaust stroke taking place at atmospheric pressure, so in this case the intake stroke while the piston is moving down will be reduced and the pressure will be less than the atmospheric pressure. Then the piston will be moving from the top dead center to the bottom dead center during the intake stroke to have the charge in this case. And then we get back to point number 1, and then we can repeat the cycle in this case. But where is actually the network out of this cycle issue? The network out of this cycle is the area contained by this region. We said the area contained by a series of process forming a cycle on the PV diagram. This area is representing the network in this case. Type this area, we said this area is the energy lost in the exhaust valve during the throttling of the exhaust valve. The gases leave under high pressure and it expands outside the engine. Then actually we have this kind of losses, which is the flow down energy. But what about the intake and the exhaust stroke? This area actually contained here between the atmospheric pressure and the intake pressure. This area is representing another kind of losses, which we call it actually the bumping losses in this case. Bumping losses is the work by the engine, the work actually applied by the crankshaft to move the piston during the intake and the exhaust stroke. Because during the intake and the exhaust stroke we don't have power, so the power is coming from the crankshaft. This piston here is connected to the crankshaft. So during the intake stroke, while the piston is coming down, in this case the piston is moving, consuming part of the power of the crankshaft. And also when the piston during the exhaust stroke, in this case it takes the power also from the crankshaft. This power during the intake and the exhaust stroke can be represented by this rectangular area, and we call it as the bumping losses. But in this case, this is a naturally aspirated engine. Naturally aspirated, that means the exhaust is leaving at atmospheric pressure, and while the piston is moving down during the intake stroke, the pressure will be reduced. Vacuum pressure will be created here. So the pressure will be less than the atmospheric pressure. And in this case, the bumping losses in this case should be a negative value. Negative value because it is coming from the crankshaft. It is not produced by the engine. But what about if we have turbocharged engine? What will be the situation here? In case of turbocharged engine, will this pumping work be positive or still it will be negative?
No, it will be positive.
So exactly.
The air
Yes.
is getting higher pressure.
Exactly. So the air in this case will be coming at higher pressure from the compressor. Like this compressor is driven, in case of turbocharger, is driven by a turbine. And this turbine, Shabab, takes this flow down energy, the energy of the exhaust gases until the pressure approaches the atmosphere. This energy will be utilized by the turbine. And the turbine will be driving the compressor. Compressor is just moving the piston to compressing the gases under high pressure during the intake stroke. This is the piston. The gases are coming here. If it is coming at pressure higher than atmospheric pressure, so this pressure will just press the piston down. Now the piston does not need actually the movement coming from the crankshaft because it is coming at higher pressure, so it will press the piston to move down. Right, what about the exhaust stroke? During the exhaust stroke, the crankshaft should be moving the piston up. Yes, and that should be a negative work. But on the other hand, we utilize actually those exhaust gases to drive the turbine here. So this energy Shabab is not lost. So it is utilized by the turbine in this case. So if you represent this cycle, and let's repeat it here. if you represent this cycle under the turbocharger or supercharged condition, so let's say from point 1 to point 2, then from 2 to 3 we have the combustion, 3 to 4, and then in this case the exhaust valve will be opening. Pressure at point 1, which is the intake pressure, is higher than the atmospheric pressure. So we'll have the expansion from 4 to 5. Point 5 in this case will be lower than point 1. And then in this case we should have the exhaust, the pressure of the exhaust under atmospheric pressure. And then in this case we can go up, and then we can have the intake stroke from, let's say, 5, 6, 7. We can have the intake from 7 to. And this area, Shabab, will be representing the pump work. But this pumping work, in this case, will be positive, will have a positive value in this case. This is in case of turbo or supercharged engines. So in turbo supercharged engines, the pumping work during the expansion and during actually the intake and the exhaust stroke, this pumping work should be a positive value. Unlike the case of naturally aspirated engine, should be a negative value in this case. Okay. طيب, those are the whole processes for the cycle. In case of the fuel, in the fuel air cycle, in case of naturally aspirated, or when we have turbocharged or supercharged engine. This part, I have drawn here for the turbocharged is not in your slide. Okay, so you may find it in your exam. By the way, Shabab, inshallah, the midterm is next Thursday, inshallah, next week, and it will be up to 2-day class. So today's class is involved in the midterm, inshallah. Okay, we said, Shabab, the cycle, the charge is air plus fuel plus residual gas. So we have some residual gases remaining inside the cylinder from the previous cycle. While the exhaust stroke, the piston will approach, as we said, the top dead center. The volume here is the clearance volume. We cannot actually force the gases in the clearance volume to go out of outside of the engine. So we should have some residual gases here. Then the intake valve will open, and then actually we'll have air plus fuel plus those residual gas. We have to define actually the residual gas fracture, which we give it a symbol X or XR. F in this case, or XR, is the ratio between the residual gas, the mass of the residual gas, divided by the total mass of charge. Total mass of charge, which is mass of air plus mass of fuel plus the mass of the residual gas in this case. Okay? The mass of the residual gas, this term we can define in terms of the volume of the gases. If you look here, we said this residual gas, just the remaining gases, and they occupy the clearance volume, the remaining gases from the previous cycle, and the volume of these gases is equal to the clearance volume. Clearance volume, which is the volume of point number 2. So this is the specific volume at point 2, or the volume at point 2, divided by the volume occupied by the total charge. If this charge, ya shabab, is allowed for full expansion until it reaches atmospheric pressure, so the volume should equal to the volume at point 5 prime. Okay, so that should be the volume of the total charge in this case. So the residual gas fracture, which is the symbol F, we give it the symbol F, is equal to the ratio between the mass of the residual gas divided by the total mass, and it should be the same ratio between the clearance volume divided by the volume if the whole gases will be allowed for full expansion in this case, is equal to V2 divided by V5 prime. And 0.5 prime, Shabab, we have the pressure at 0.5 prime is equal to the pressure at 0.5, which is equal to the atmospheric pressure. And the entropy at 0.5 prime is equal to the entropy at 0.4, because it continues isentropic expansion in this case. Okay. In some cases, Shabab, we do have some exhaust gas recirculation. So in addition to the residual gas, we take part of the exhaust gas and just introduce it again through the intake valve. So why we should consider in some application, if you have some exhaust gas recirculation? Why we do that?
I believe to lower the temperature.
Exactly. So in this case, to lower the combustion temperature, and in this case, we can lower the emission, especially the emission of NO and NO2, which we call them the NOx emission. So in some cases, we take part of the exhaust gases and return them back through the intake valve. In this case, we define another parameter, which is actually the burned gas fraction. Burned gas fraction is the mass of the residual gas divided by the mass of the exhaust gas recirculation divided by the total mass of the charge. Total mass of the charge, which is mass of air plus mass of fuel plus mass of residual gas plus mass of exhaust gas recirculation. Okay? But if we have a mass of exhaust gas recirculation is equal to 0, that means in this case, the burned gas fraction, XV, will equal to the residual gas fraction, F in this case. But anyway, شباب, we will not go in deep in the analysis of this cycle. That should be enough, but let's define the efficiency of this cycle. The efficiency is the net work out divided by the heat added. Heat added due to combustion is equal to m dot fuel multiplied by the heating value. If we assume that we have 100% combustion efficiency, so all of the energy content, chemical energy content of the fuel will be converted to heat in this case. And based on that, we can say the eta, indicated thermal efficiency, will equal to work net plus, which is the expansion work plus the compression work. But this work we have calculated usually kilojoule per kilogram air. So we have to multiply by here by mass flow rate of air. This is divided by the heat added for efficiency of combustion 100%, because the combustion efficiency is equal to the heat added divided by m dot fuel multiplied by the heating value. If this efficiency we assume it 100%, that means the heat added should equal to m dot fuel by heating value. So we assume 100% combustion efficiency. So all fuel will be burned. So it will be m dot fuel multiplied by the lower heating value of the fuel. But actually we do have some residual gases, so which should affect actually the combustion of the fuel. So in this case, to balance this equation, we have to multiply here by 1 minus F. F is the residual gas fraction in this case. So the indicated thermal efficiency will equal to m dot air multiplied by the expansion work plus the compression work divided by m dot fuel multiplied by 1 minus the residual gas fraction multiplied by the lower heating value in this case. If you divide by the mass flow rate of air, so it will be the expansion work plus compression work divided by fuel to air ratio actual multiplied by 1 minus the residual gas fraction multiplied by the lower heating value in this case. And this term, fuel to air actual, is equal to what? Fuel to air theoretical multiplied by the equivalence ratio. So this term is equal to fuel to air theoretical multiplied by the equivalence ratio. Now you can see that this indicated thermal efficiency is function of what? Expansion and the compression work, those are function of the compression ratio. So this efficiency is function of the compression ratio. Also it is function of what? Function of the equivalence ratio, and it is function of the fuel to air ratio in this case. So this efficiency for the fuel air cycle can give us actually a more reasonable value for the thermal efficiency of the engine in this case compared to the air standard cycle. Air standard cycle for eta thermal Otto cycle for the air standard cycle is equal to 1 minus 1 over R to the power K minus 1. So this efficiency can give us indication only about the effect of the compression ratio. But here, considering the fuel air cycle, it can give us indication about the effect of the compression ratio and also the effect of the fuel to air ratio or the effect of the equivalence ratio in this case. Okay. One main also characteristic of this cycle is that the specific heat is variable. So in the fuel air cycle, we consider variable specific heat. So the specific heat is not constant. That means the value of K is not constant in this case, which is CV over CV. So one of the main characteristics of the fuel air cycle is that we consider variable specific heat. I cannot say about the expansion work is equal to U3 minus U4 In the air standard cycle, I consider this equal to CV multiplied by T3 minus T4 because we consider this specific heat as constant. But no, in this cycle, we cannot say that. We have to consider it U3 minus U4. And usually, شباب, to put those values, U3 and U4 and U1 and U2, we have already some tables. If you want to look at, you can just consider the chapter, I think chapter 4 in the book by G.B. Herold. They are considering actually some experimental data for isooctane C8H18. They have presented actually those data in terms of a chart as function of the equivalence ratio and as function of the temperature through the cycle. Then we can calculate the internal energy U3, U4, U1, U2, and then we can calculate the expansion work, and also we can calculate the compression work, which is U1 minus U2. So in this case, if you have the analysis of the cycle, depend on the experimental measurement. We have to do the experiment for a certain kind of fuel. I think only in G.B. Herold they have considered only this fuel, the data for this fuel. And in this chart, we can calculate the internal energy as function of the equivalence ratio. Then we can calculate the expansion work, compression work, come here and substitute in the indicated thermal efficiency to calculate the thermal efficiency in this case. Okay, so the variable specific heat approach, we don't consider the specific heat as constant. So in this case, we have to get those values based on the experiment in this case. But the efficiency in this case should be lower or higher than the case of air standard cycle. Should be lower or higher? It should be lower, exactly, Shabab. So in this case, we are coming actually close to the reality. So in this case, the efficiency should be lower than the case of air standard, cycle. If you look here, Shabab, this is what we have defined. This is the effect of the equivalence ratio. Usually the efficiency, Shabab, is maximum. If you look here, this is the efficiency is function of the fuel to air actual, which is fuel to air theoretical multiplied by the equivalence ratio. So we have the equivalence ratio here down. If the equivalence ratio is reduced less than 1, that means we are what? Less than 1, that means we are lean or rich. If phi is less than 1, we have rich combustion or lean combustion?
We have
lean combustion in this case. So if phi is less than 1, this value is reduced. That means the thermal efficiency will be increased in this case. That means we can get maximum thermal efficiency, Shabab, for the engine when it is working under lean condition, but not much lean condition. It should be about, if you look here to this chart, you will find the efficiency. First of all, the efficiency increase with the compression ratio. This is by default because the network of the cycle, if we increase the compression ratio, this network area will be increased. So the efficiency should be increased in this case. But when you look here when they look at the efficiency as function of the equivalence ratio, so we can get maximum efficiency for a gasoline fuel, C7H17. This can also consider a kind of gasoline fuel. The efficiency will be maximum when the equivalence ratio is equal to 0.75. If I consider it much actually lean in this case, much leaner conditions, that means, Shabab, we have more diluent, more air, and this will absorb actually part of the heat transfer. So the heat added will be reduced in this case, and the efficiency will be reduced. So the efficiency is maximum in the lean zone, but in the lean zone, very close to the stoichiometric condition. We cannot go much lean in this case. And also we cannot go rich. If you look here, rich, which is the equivalence ratio is greater than 1.3. That means we have lambda is less than 1. So that means we have less air. Less air, that means we have incomplete combustion in this case. And also the heat added will be reduced in this case, and the thermal efficiency will be reduced. Okay. So this is, Shabab, also as you can look here, the break mean effective pressure or the indicate mean effective pressure. We can define it, Shabab. Indicate mean effective pressure is defined as what? The network expansion plus compression divided by V1 minus V2. V1 minus V2, which is the displacement volume of the engine in this case. Okay. So here, Shabab, all what we can say about the fuel air cycle. Here is an example. it will be a homework example, but it's a good one to practice. This will be your homework. I will announce inshallah today. If you look at this homework, we said for the fuel air cycle, we said the specific heat is not constant. So we cannot say delta U is equal to CV delta T. But let's take this assumption for the fuel air cycle. Let's consider the specific heat as constant. And we can say delta U will equal to CV multiplied by delta T. And let's consider an engine fueled by gasoline engine. We have normal iso-octane fuel C8H18. And we need to calculate the net power output of this engine. And then we need to compare it when we have hydrogen addition. When we have the fuel is a mixture of 80% iso-octane plus 20% hydrogen. And we need to see the effect of hydrogen addition on the network out and also on the thermal efficiency of this engine. So let's consider the basic case, Shabab. If we have a fuel, pure fuel, which is pure iso-octane, C8H18. So let's write down the combustion equation. He said this under stoichiometric condition, so lambda is equal to 1 by gamma, which will be 12.5 O2 plus 3.76 N2. That will give us CO2 plus whatever. Okay, those are the combustion product. You can write down this combustion equation. So this, when we have the fuel, is pure iso-octane. Type, we say the specific heat CV and CV are not constant. Let's assume those are constant. But those are Shabab CB and CV for the mixture. Okay. In case of air standard cycle, we consider CB and CV for the air. We don't have mixture because we don't have aslan working fluid. The working fluid was just air. But here the working fluid is air plus fuel in this case, plus some residual gas. Let's assume the residual gas mass is equal to 0. So we have the residual gas fraction is equal to 0. We don't have residual gas. Okay, and I give you in this case the mass flow rate of air. It is given to you. You can look here, close to the end, the mass flow rate of air. Yes, here. This is the mass flow rate of air is given. So this is given kilogram per second. Depending on the engine speed, we can calculate the mass flow rate of air. Anyway, when we take the engine performance, inshallah, we will learn how to calculate the mass flow rate of air. But anyway, at this stage, mass flow rate of air is given. Okay. But can we calculate from this combustion equation? Can we calculate the air to fuel ratio, which is mass flow rate of air divided by mass flow rate of fuel? We can calculate the air to fuel ratio based on the combustion equation. Then from this we can get the value of the mass flow rate of fuel. I'm actually solving the homework, but just I'm trying to give you some guide. This homework, Shabab, is based on constant specifically, but still we are following the fuel air cycle. Okay. But in this case, if I need to calculate the compression work, it will equal to mass flow rate of air plus mass flow rate of fuel multiplied by U1 minus U2. And this U1 minus U2, we can replace it by CV for the mixture multiplied by T1 minus T2. But CV for which mixture, Shabab? During the compression stroke. Do we have burned or unburned gases? Unburned gases, which are what? Those unburned gases, which are the fuel plus the air in this case. So these are our mixture during the compression stroke. We have a mixture of fuel plus oxygen plus nitrogen in this case. But at state number 2, how we can calculate first of all, Shabab, CV and CV for the mixture. Also for this compression process from 1 to 2, how we can calculate the temperature? This is isentropic. So T2 over T1 will equal to B2 over B1 to the power K of the mixture minus 1 divided by K of the mixture. That should be the same as V1 over V2 to the power K of the mixture minus 1. V1 over V2 is equal to the compression ratio, R, which is given also here. The compression ratio for this gasoline engine is 8.5. So I have the compression ratio. I'm giving you B1 and T1. Then you can calculate T2 and B2. But we need to calculate the value of K for the mixture. K for the mixture, which is the specific heat ratio, is equal to CV for the mixture divided by CV for the mixture. So K for the mixture is equal to CV for the mixture divided by CV for the mixture. And CV for the mixture, as we have learned from chapter 2, I think, or 3, is equal to the summation of mass fraction multiplied by CV in each component. For process from 1 to 2, the mixture is air plus fuel. We have here the number of moles for O2, N2, and fuel. Then we can get the mole fraction for each actually species, for fuel and for O2, for N2. Get mass fraction, then we can convert it to get the this is the mole fraction. Convert it to get the mass fraction. We have mass fraction is equal to the mole fraction Yi multiplied by the molecular weight I divided by the molecular weight of the mixture. And molecular weight of the mixture is summation of Yi molecular weight I. Anyway, convert it to Xi. Then we can sum up the CV for the mixture with summation of Xi mass fraction multiplied by CBI. CB for each component, for the fuel, for O2, and for N2, we can get it from table A1. Table A1, you will find the value of the specific heat for different fuel and also for some gases, including O2 and N2. Then I can calculate CB for the mixture. I need to calculate CV for the mixture. We can just say CV will equal to summation, like CV will equal to for the mixture, the same summation of Xi, CVI. Or we can have the relation CV will equal to CB minus R. If I calculated CB for the mixture, I have to calculate R for the mixture. R is equal to summation of Yi, Ri. And also the value of the gas constant R, we can get it from table A1 for each gas. Okay? Then we can calculate CV. Anyway, you can do through all of this. Calculate CV for the mixture. So the expansion work, where it has gone. So it gets a little complicated. So let's say for the expansion work, the compression work, sorry, will equal to M dot air plus M dot fuel multiplied by CV for the mixture multiplied by T1 minus T2. And the expansion work similarly, but the expansion will be the burned gases. The mixture in this case will be the combustion problem for the process from 3 to 4. But still the charge is M dot air plus M dot fuel multiplied by CV for the mixture. This mixture is the reactant. Here this mixture is the product multiplied by T3 minus T4. And also we can link 3 and 4 similarly like this one. It is isentropic, and also we can get it function of the compression ratio. Calculate the K for the mixture and CV for the mixture for the product in this case. Then we can calculate the expansion work. Then what about the temperature T3? I need to get the temperature T3. T3 is equal to the adiabatic flame temperature based on U product. The first law analysis, U product is equal to U reactant. So just to do this based on this combustion equation, then you can calculate the temperature T3, which should equal to the adiabatic flame temperature. So you will consider the combustion equation, apply the first law, then we can calculate the maximum cycle temperature T3. Then from 3 to 4, you can say T3 over T4 is equal to V3 over V4, as we used to do, K minus 1 over K. This is K for the mixture. And the mixture is the product in this case. And then at the end, we can calculate the net work, which will equal to rate of net work, work dot expansion, plus work dot compression. This is the rate of work, because we have considered here the mass flow rate of air and mass flow rate of air. So the rate of net work out will equal to work dot expansion divided by plus work dot compression. And the cycle efficiency will equal to what? Cycle efficiency will equal to work dot expansion plus work dot compression divided by M dot fuel multiplied by the lower heating time. Okay, Shabab? But this is for the case of what? The fuel is pure isooctane. So let's consider the next case when we have enrichment with hydrogen with 20%. 20% hydrogen and 80% isooctane. C8H18. So let's write down the combustion equation. It will be 0.2 of hydrogen plus 0.8 of C8H18 plus air. Lambda is 1. Calculate gamma. You have learned how to calculate it for a mixture of fuel. Write down the combustion equation again. Repeat all what we have done. And then again you will be calculating the net work, expansion, and the compression divided by m.fuel by lower heating value, and calculate the thermal efficiency. And by this, you can see the effect of hydrogen addition. When we add hydrogen, what will happen to the thermal efficiency? Will hydrogen enrichment improve the thermal efficiency or not? But in case if we have fuel mixture, the lower heating value is equal to what? Is the summation of the mass fraction of each fuel in the fuel mixture multiplied by its lower heating value. Here, this is by volume. 0.2 H2 and 0.8 C8H18. Convert it by mass for the fuel mixture, not the whole mixture, fuel plus for the fuel mixture only. Convert from mole fraction to mass fraction. Then calculate the lower heating value for the fuel mixture, as we have learned, is equal to the summation of the mass fraction of the fuel, of each fuel in the fuel mixture, multiplied by its lower heating value in this case. But keep in mind that we have write down the combustion equation per 1 kilomole of the fuel. So you should have some kind of conversion here. Do this, and compare it. When we have hydrogen addition, what will happen in this case to the thermal efficiency? Okay. Is it a good example for the homework? So it's long, but you will learn. You will learn something. That based on this theoretical analysis, we can calculate the maximum cycle temperature and maximum cylinder pressure inside the cylinder. We can calculate the network out, and also we can calculate the thermal efficiency. And also we can see the effect of hydrogen, which is a parameter actually that is very important in the analysis. In all future engine, actually hydrogen is the future fuel. Okay. But usually hydrogen in internal combustion engine does not result in much addition. Usually hydrogen, when we use it in the fuel cell, inshallah we'll be talking about this in the last chapter, can result in an efficiency of about 60%. So here the internal combustion engine, the efficiency is around the maximum 35%. So why I should use hydrogen in an internal combustion engine to burn it by combustion and give me efficiency about 35%, while I can use this hydrogen in a fuel cell, and the fuel cell will be working at efficiency more than even 60%. And it will generate electrical power. Then we can just take this electrical power and then we can drive the engine. Drive it to give you this electrical power to electric motor, and the electric motor can drive the engine in this case. And Toyota have already produced a series of versions of the fuel cell car, which is working based on the hydrogen fuel cell. Okay, and this is the story. Inshallah, we'll get into touch to all of that. Inshallah, by the end of this course, I will be talking about the fuel cells and the different kind of the fuel cell. Also, I'll be talking about the electric vehicle in this case. Is that clear, Shabab? So this homework, inshallah, will be announced maybe today or something. Okay. Is it clear, Shabab?
Yes, sir.
Now it's getting little interesting, so we can get something out of our theoretical analysis. We can link it to the internal combustion engine, and we can see some effect. We can see the effect here of hydrogen addition, how it can affect. We can calculate this, how it will affect actually the thermal efficiency of the engine. But to end up with the engine cycle, we have to move to the actual cycle in this case. We talk about the air standard cycle. We said all of this cycle is actually reversible. It does not take care of the effect of fuel. We don't have valve. We do have a lot of assumptions. So the efficiency will be the maximum, but it does not take care actually of a lot of other parameters. The fuel air cycle, we consider some cases close to the reality. We have considered the intake and the exhaust valve. we have considered the charge as air plus fuel in this case, and we have calculated based on that the thermal efficiency, which should be very close to the reality, and we have considered the combustion as well. But some of the assumption in case actually of the fuel air cycle that we have in this case the combustion is instantaneous, but that this actually does not represent the real case. If you look at this is the standard Otto cycle. The real case actually we don't have combustion instantaneous. We do have ignition before the top dead center, and then the volume, in this case the pressure will be increased, and the combustion will take place actually, but not at constant volume. So that means the peak pressure, the value of the peak pressure will not be at the minimum volume, which is at the top dead center. So the peak pressure will take place during the expansion stroke, while the piston is going down. That means the peak pressure value will be reduced in this case, because it does not take place at the minimum volume at the top dead center. We call the combustion in this case as progressive combustion. It is not instantaneous. Instantaneous combustion, that means the combustion takes place at no time, when the piston is at the top dead center. In case of actual engine cycle, the combustion just takes some time. We call it progressive combustion, because the gases need mixing, and the combustion itself needs some time to take place. So the combustion takes place, we initiate the combustion before the top dead center, but the combustion does not occur actually instantaneously, it just takes some time, and the pressure will take some time to be raised, and in this case, the maximum cycle pressure usually will be attained during the expansion stroke. But during the expansion stroke, the piston is moving down, so it is trying to reduce the pressure. That means the maximum cycle pressure in this case will be reduced in this case. Also, the second assumption we have considered all processes, compression and expansion processes in the fuel air cycle as isentropic. Isentropic, that means reversible and adiabatic. Reversible, that means we don't have any losses, we don't have friction losses, we don't have heat transfer losses. And the process is adiabatic, we don't have heat losses. So this is actually does not represent the real case of the engine. In the real case of the engine, we should have some heat transfer. In the fuel air cycle, we assume actually that all processes are adiabatic. We don't have heat transfer. But in the real case, we should have heat transfer significantly during the expansion stroke, during the power stroke, after the combustion process. Some of the heat will be actually absorbed by the cooling water, which should be surrounding the engine in this case. So in the actual cycle, if this is the engine, and this is the intake valve, and this is the exhaust valve, once we have the combustion here, so the heat will be released, and here around this engine we should have cooling water. So for the real cycle, some heat will be actually lost to the cooling water, and also some heat will be absorbed by the cylinder heat here. And through this cylinder heat, we have actually the oil, the oil ring and the pressure ring, especially the oil ring. It will transfer actually part of this heat also to the oil, the lubricating oil in this case. So the engine in this case is not adiabatic. So the assumption that the heat transfer is equal to 0 does not apply in the real case. So up to now, we have three differences. Compression and expansion process are not isentropic. This is actually the processes are not reversible. We should have some losses in terms of friction losses. Usually about the friction losses in the internal combustion engine, it can result about 30% of the losses. This is the friction losses, especially at high engine RPM, actually more than 2,500, the friction losses may raise to up to 40%. Okay. So we should have some losses. So the isentropic compression and isentropic expansion are not representing actually the real case in this case. So the process, expansion and compression are not isentropic. Combustion does not take place instantaneously. As you can see, the combustion is progressive combustion. So the maximum cycle pressure will not be attained at the top dead center. The process are not adiabatic, so we should have some heat losses. And also the blowdown energy is actually bigger than the case of the fuel air cycle, the energy losses in the exhaust valve. Because in the real case, the exhaust valve does not open at the bottom dead center, like the fuel air cycle. In the fuel air cycle here, I just removed it from the board. You can see at point 4, the exhaust valve open at the bottom dead center. But here actually in the real case, we have to open the exhaust valve before the bottom dead center, so that we can have higher pressure to be able to exhaust or scavenge exhaust gases in this case. Okay, so in this case, if I open the exhaust valve early, that means in this case the blow down energy will be increased in this case, and it will be higher compared to the case of the fuel air cycle. And based on this, we can define three kinds of losses, or three factors of losses. We can define the time loss factor, three factors for the actual cycle. We can define the time loss factor. Time loss due to what, Shabab? Which process does it need time in this case? Which process the combustion take place, which is actually progressive combustion in this case. But in case of fuel air cycle, it is instantaneous combustion. So in this case, there is a time loss factor, that the combustion is progressive and it needs the time, and this will result actually in more losses. We have another factor, which is the heat loss factor. We have some heat is lost out of the engine due to the cooling water. The case is not adiabatic like the case of fuel air cycle. And we have actually blow down loss factor, the blow down energy due to actually the early opening of the exhaust valve. We should have more blow down energy in this case. If you look at the time loss factor, if you have on the PV diagram, if this is the top dead center, and this is the bottom dead center. This is the compression stroke, let's say from point 1, we should approach the top dead center. Before the top dead center here, we should have the ignition. The spark should be initiated. Once the spark is initiated, the process does not continue in this direction. Just the pressure, once the combustion is initiated, the pressure will be raised. Suddenly the pressure will be raised. And then the piston will be approaching the top dead center, and the combustion will be continue in this case. The combustion will take place, part of it, during the expansion stroke, until we reach this point at which we should have the maximum cycle pressure in this case. Okay, but this maximum cycle pressure, if we compare it to the instantaneous combustion in case of the fuel air cycle, in which the combustion will take place under constant volume at no time, instantaneous combustion, this peak pressure will be less than this value. The peak pressure here, this is for the fuel air cycle, and this is the actual value for the actual cycle, because the combustion takes time, and the maximum pressure does not actually take place at the minimum volume, not at the top dead center. That's why we should have the pressure, in this case, maximum pressure should be reduced. And then we can have the expansion. If this expansion is isentropic, it should approach actually a point less than 0.3 here. Okay, but it is not isentropic. But here, Shabab, we set the area on the PV diagram. Area contained by the cycle should be representing what? The net work. But here you can see, as we initiate the combustion before the top dead center, we will not continue here up to this point. Just the pressure will be raised in this case. So that means this area is area lost from the work due to the progressive combustion. In addition to what? In addition to this area as well. Because actually the pressure, maximum pressure, is less than the maximum pressure in case of the fuel air cycle. So these two areas can be related to, those losses in the network are related to the time loss factor due to the progressive combustion. But here, the expansion will take place. The expansion here will take place until we reach this point. Anyway, yeah, if I will be talking about this point about the blow down, and I will draw another figure right now because there are a lot of complications here. Okay, but this is the process, Shabab. If you represent the fuel air cycle, so that should be the isentropic expansion from 3 to 4. From the maximum pressure 3 until we reach 0.4. But for the actual cycle, this is the cycle. So this is the maximum pressure. And then we should have the expansion in this case. This is the representation of the actual cycle. So there is a difference here, Shabab, in the work also, in the network. This difference is due to what, Shabab? Let's get from your side. Exactly. So this difference is due to the heat losses. Because actually during the expansion stroke, some of the heat will be rejected will be absorbed by the cooling water. Okay, so this difference in the network is related to the heat losses. Yes? Is that clear يا شباب?
Yes.
So we should have time loss factor due to the progressive combustion, which need times to take place, can be represented on the PV diagram by those two areas. And then we have heat losses due to actually the heat losses. We have network losses due to the heat losses to the cooling water and the lubricating oil in this case. And this يا شباب can be related to the heat loss, what we call the heat loss factor in this case. But what about the blow down loss factor? If you look at the blow down energy, it's represented here. This is the top dead center and that is the bottom dead center. During the expansion stroke. Here شباب, at this point we have to open the exhaust valve before the piston approaches the bottom dead center. Why we should do that شباب? Why we should open the exhaust valve before the piston approaches the bottom dead center? Why we should do it? Why we don't open it at the bottom dead center? Like the fuel air cycle. In this case, شباب, the pressure here at this point inside the cylinder pressure is about 7 bar. Okay, this we call it early opening of the exhaust valve. If I open the exhaust valve early here, that means the pressure here, I will be losing this pressure during the expansion stroke. Because if I delay this opening of the exhaust valve, in this case we can benefit more expansion work. But I will open the exhaust valve, that means the pressure inside the cylinder will be relieved. And in this case, due to the early opening of the exhaust valve, in this case the pressure, instead of going in this direction, the pressure will just drop down this way. Okay? The pressure will drop inside the cylinder, and in this case I am losing this additional part of work during the expansion stroke. But if I open the exhaust valve at the bottom dead center, when the piston is at the bottom dead center, I went this way. So in this case we benefit the pressure during the expansion stroke. But when you open the cylinder, the exhaust valve, when the piston is at the bottom dead center, the pressure here شباب is low. It's very close to the atmospheric pressure. So in this case the gases inside the cylinder are not under pressure. So when you open the exhaust valve, those gases, in this case the piston is at the bottom dead center. Those gases need power from the crankshaft to push the piston, then the piston can push the exhaust gases outside. That means in this case the pumping work will be increased. Okay? And if you do that, open the exhaust valve at the bottom dead center, that will be the kind of expansion. And then we have to go through we have to go through this way. And then we have to go through the compression stroke. And in this case, more work will be needed in this case by the piston, to be done by the piston on the exhaust gases, to just force the exhaust gases to leave the engine. So we have to apply more work. But if I open it early, the gases under high pressure will be forced to go under the pressure difference without the movement of the piston. So it will reduce this power. This is the difference between the power needed by the piston in both cases. But usually we don't need any شباب also to open it either early or to open it actually too late when the piston is at the bottom dead center. Usually we open the exhaust valve at a point in between, which is a kind of optimization, so that we don't lose the cylinder pressure. In this case, we open it when the cylinder pressure almost at about 3.5 bar, not 7 bar. So we wait until the pressure is almost about 3.5 bar, and in this case the expansion will be a little bit in between both of them. Okay, so that in this case we can just reduce the blow down losses, in this case. Is that clear, شباب? So if I open the exhaust valve early, the pressure inside the cylinder is 7 bar. So in this case I will be losing this pressure during the expansion stroke. So it is losses of the expansion work. But if I open it late, that means in this case I need more power from the crankshaft to scavenge the exhaust gases, because they are coming actually under low pressure in this case. If we just try to optimize in between, then in this case we have to open the exhaust valve when almost the pressure is about 3.5 bar. You can look at this one here. And in this case, if you have the optimum angle at which the exhaust valve should open, it should be between 40 and 70 degrees before the bottom dead center. That should be the optimum angle for the minimum blow down energy, blow down losses in the exhaust gases. The exhaust valve should be opening about 40 to 70 degrees before the top dead center in this case. Okay. طيب here you have all the losses. You can look at this cycle. Here is the losses within the engine. We have time loss factor at this point and those parts. This is time loss factor due to the progressive combustion. Combustion needs the time, and that's why we don't approach the maximum pressure within the cycle in this case. That will result in losses of the network of about 60%. And also we have heat transfer to the cooling water, and this is the biggest portion. It is about 12% of the losses of the engine. And then we have this is actually the blow down losses, the losses due to early opening of the exhaust valve before the bottom dead center. Anyway, Shabab, we have to open the exhaust valve before the bottom dead center, so that we can have enough cylinder pressure to scavenge the exhaust gases. And that should result in about, at the optimum case, about 2% of the losses within the engine. And this, Shabab, is the representation of the PV diagram for the actual cycle, considering the Otto cycle in the case of a gasoline engine, representing the three kinds of losses. We have the time loss, we have the heat loss, and we have the blow down energy in this case. Please revise those figures. You will find, for sure, you will find them in your in the coming exam. But yeah, Shabab, I'm not relating the case to the exam. This is actually something very important to the analysis for the fuel air cycle. As you can see here, this is the cycle that I have drawn. Also, Shabab, the expansion here is not isentropic. Okay, so the specific heat ratio is not constant. Okay, if it is isentropic, we have to follow this dotted line. Okay, but it is not isentropic. So also we should have some losses. The difference between the dotted line for the expansion and this line, the bold line, this difference, Shabab, is due to the difference in the specific heat. So if the specific heat is constant, it should be almost isentropic. But the specific heat for the actual cycle is not constant, because the specific heat is function of temperature. Even for the ideal gas, it is only function of temperature, and the temperature during the expansion stroke is changing. That means the specific heat will be changing in this case. So, anybody is asking?
Yeah. Is there a way to calculate these losses, the factors I mean?
Yes, this is what, yes, this is, as we said, for the blow down energy, we can optimize it just in between. We don't open the valve too early, we don't open the valve too late, so that we can just try to optimize it. But anyway, Shabab, we have to have this kind of loss for the heat losses. Is that your question, Ali?
No, my question is, how do we calculate these factors?
Actually, there is no theoretical way to calculate it. The theoretical analysis, that's why, Shabab, we started with the air standard cycle to try to develop some equation to calculate heat added, heat rejected. We went to the fuel air cycle, and I told you in the fuel air cycle we have to have experiment, and also like this for the actual cycle. For the actual cycle, it has to be based on the experiment. I have to measure the pressure at which the exhaust valve is opening, and then in this case we can get expectation. We can draw the cycle, Shabab. You can put a pressure transducer here at the top of the cylinder. It will measure actually the pressure inside the cylinder. Pressure against the crank angle, the movement of the crankshaft, the crank angle. We can translate this crank angle in terms of volume, and we can plot the pressure against the volume, and then we can calculate the network. This is how it go actually in the real case, but we don't have a Shabab theoretical equation in order to calculate this work in this case. Now in this case for the actual cycle, I'm talking about the kind of losses that we should have, and we have to optimize them, just to try to reduce them. And also the heat losses, as you can see, can we just remove the heat losses part? Can we just get rid of the cooling water? No,
No,
the engine will,
material. Yeah.
sure, the engine will not be working in this case. So this is the case of internal combustion engine. We should have some losses. Heat losses, heat transfer losses is about 30%. Friction losses is about 30%. And there are some kind of 10%, some other losses like lubricating oil and some other losses, sudden losses due to combustion and so on. And then you can get about 30% as a power output. So 30% of the fuel energy, which is M dot fuel multiplied by the lower heating value, yeah, only 30% out of it we can get. Okay, so this is the case of the actual engine. But what about the time loss factor issue? I didn't talk about this. Time loss factor. This one, as we said, due to progressive combustion. Progressive combustion, the combustion take place before the bottom dead center, and it needs the time actually to take place. We said based on that the maximum cycle pressure will be less than the case of fuel air cycle. But is there a way to just try to raise the maximum cycle pressure here? Is there a way, Shabab? Through what? Through spark? Spark advance.
Yeah.
So if we advanced the spark, started the ignition a little bit earlier during the compression stroke, then in this case we can optimize this maximum pressure to take place at the minimum volume, at the bottom, at the top dead center. So yes, I know the combustion does not take place at constant volume, it's a progressive combustion. But it will be progressive combustion this way, so that actually we can attain the maximum pressure at the top dead center. Maximum pressure at the top dead center, that means in this case, the expansion will start from higher pressure, and in this case, this part of the work will be added in this case. So if we just advance the combustion, you can look here. If we have the ignition is at the top dead center, the combustion will take place during the expansion stroke, and that should be the maximum pressure. Okay, and then we have to have the expansion compared to the fuel air cycle. Fuel air cycle from 2 to 3, you can see the maximum pressure here is at this point. So there is a huge difference in the maximum pressure between the fuel air cycle and the actual cycle. In case actually if we have the ignition, the spark, we have the spark at the top dead center. Now look here, when we have the spark 35 degree, which is the optimum value before the top dead center. In this case, the combustion will be progressive, take place this way, but we'll optimize it to have the maximum pressure at the top dead center when the volume is minimum. Now you can see the value of the maximum pressure for the actual cycle. It can be very close to the case of fuel air cycle. 0.3 prime is very close to 0.3. Now we can start the expansion from high pressure. You can see, Shabab, the difference in the network area. It has been increased in this case. What about if we advance the spark a little bit more? So if it is good, then in this case we can go with more spark advance. So what will happen, Shabab, if we have more spark advance in this case? If we have advanced the spark a little bit more, we have early advance.
It will reduce the area.
It will, in this case, not related much to the area, but if we have here, Shabab, if we started the ignition earlier here, let's say at the middle of the compression stroke. Ignition, that means we have combustion, we have heat release. That means the pressure will be raised and the temperature will be raised. And during the compression stroke, the power is coming from the crankshaft, trying to push this piston upward inside the cylinder. So let's draw it here. During the compression stroke, this is the piston, the cylinder, and the piston is here. During the compression, the power is coming from the crankshaft, trying to push this piston up. But if I initiated the combustion too early, we have to have heat. The heat of combustion, the gases will be burned, and the pressure in this case will be raised. Pressure will be raised, it will be resisting the movement of the piston in this case. So we will need more power from the crankshaft in order to compress the burned gases. Because this burned gases results in higher pressure and it will actually resist this movement. And this is a kind of direct loss. This is a direct loss of the engine. Because in this case, if you will be able to get higher pressure, it's okay. But in this case, actually, the work during the compression will be increased. The cycle will be going more sharp in this case. So it is advised to have early ignition, but in order to get the maximum pressure at the top dead center, and that's it. If you did actually more earlier ignition, then in this case you will be actually, it will be a direct loss, because in this case you will need more work during the compression stroke in order to move the piston, because in this case we have above the piston we have burned gases in this case. Okay, is that clear يا شباب? Is it clear?
Yeah.
طيب يعني this is يا شباب all what I want to say about the engine cycle. Inshallah next time we'll start يعني a new chapter. I will be talking about turbocharged and supercharged engine.